State estimation part 4. So what we're going to do now is take the same diagram we had from part 3, where we have a nonlinear discrete time Kelvin filter, but where our updates or our measurement comparison is just subtracting and our updates are just adding, and we're going to change those to be arbitrary functions. Well, not completely arbitrary, but nonlinear functions are just addition or subtraction. So let's in here use S, since it's subtraction, use S over here. But what we're going to be doing is comparing Zn plus 1 and Z hat n plus 1. So for example, with quaternions, instead of subtracting the quaternions, you'll divide the quaternions. Just one example where you'd use that. And then over here, when you have a residual that gets multiplied by your gain matrix to get update, I'll just use delta over here. To get an update delta, instead of just adding it, you would do correction term. So what's this? Use C for correction of x hat n plus 1 minus delta. And in doing all this, we're redefining what the error means. And what the error means and what the correction is highly linked, in that if the correction term coming in, if your delta coming in is the error, then you'll get corrected in that one step. So I'm going to redefine the errors here instead of just subtracting the two.
So quick question.
Yep.
What does this do that changing K can't?
What it allows you to do is, let's see here. Well, what it allows you to do for quaternions, for instance, a quaternion that has no rotation is 1, 0, 0, 0. Okay? That means if you have an orientation, and if you have two orientations, and you want to know the quaternion to get from one to the other, you take the quaternion of the first, multiply it by quaternion, and you get to the second. If they're exactly the same, this is kind of your error right here, right? And since this isn't 0, it has a 1 here. That's why you have to do this sort of, one of the reasons you have to do this sort of thing. You can't just, since you can't just subtract quaternions and get 0 if there's any error, you have to multiply. It's a multiplicative error. That's pretty much why you have to do this sort of thing. K is kind of unrelated to whether or not you do this or not.
Okay, and then similar question. If we have these full equations at either end of that chain, why is K still there? Or is it necessary?
Well, you could subsume K into S.
Okay.
K is kind of the parameters you get to tune and how fast you want
Okay,
your
so
response.
that's still where we put our twiddly knobs. The stuff
Yeah,
that stays in the
exactly.
purple box is consistent.
Yeah. Okay, so now we're going to redefine our errors. Instead of subtracting them, we're going to just make it be a function of the two values. So error is going to be this function d, or think of it as being difference. Unit when you're just doing the typical one. So xn plus x hat. So error n plus 1 plus, so the error between these two guys is going to be this function d. Of the two values. And so your error with the minus will be when you're comparing these two, and the error with the plus is when you're comparing these two. Okay. But now we have certain constraints, which are going to be that. So let's see here. So E. Your error is this d function, x and x hat. Okay. But x, what I said about C kind of really defining your error, we want it so that if you have, let's see here. If you take your estimate and you correct for your error, you should get the true value. Okay, and your error is defined as the difference in some sense between the true value and your estimate. Right. So, putting these together, we have the constraint that x equals c of x hat comma d of x comma x hat. Right, so your C and D functions are kind of inverses of each other in this sense. So for example, when we just had subtraction, your error was subtracting the two values, but your correction was adding the two values. So again, if the exact error comes through here and gets to here, then it should correct to be the true value. Okay, and then another constraint we have is on this guy. If you've got your two sensor readings and they're exactly the same, the output of this should be 0. So S of Z comma equals 0. That might not be right because the question someone just asked previously. You know what? This doesn't come to place, so don't worry about that. Not sure.
Probably not sort of quaternions, right?
Right, because if you're
Quaternion like so as well.
right, yes. So you don't have. Never mind. Forget that constraint. Okay. So this is a constraint you have though, and also. Okay, well we also have the constraint that if you correct x with 0, that just should equal x. But you know what? Again, that's not even true with okay, forget about those constraints for now. Put the question mark up here. When we get to those. Okay, but this has to be true. If you take the difference, if you find the error and you correct for that error, you should get the true value. All right, so we changed this from subtraction to some function, this from addition to some function, and define the difference.
And F and C should be the inverse of each other.
What's that?
They should be the inverse operation.
S and C are not. D and C are the inverses of each other in this sense. S is not going to be because it's taken measurements rather than states and doing something with them, and the measurements might be some weird function of the states.
So roughly what form do these functions take, or is that not standard?
It's whatever your dynamics are, right? So, yeah, could be anything.
Not too complex, hopefully.
Yeah, hopefully they're pretty smooth and somewhat linear or linearizable about a point, so that all this math actually works.
Basically, want continuous function.
And let's maybe in the next part 5, maybe we should do some examples.
Okay, I'm going to ask you to describe one more time, like what the dynamics that each of these functions are relating to is.
Okay, yeah.
Just very roughly.
Let's just go through it once more. So the red stuff is your real system.
Yep.
The blue stuff is your simulated system.
Yep.
The purple and purple and green are your update.
Yep.
So you take U as your state input, so like your motor torques or whatever. W is some disturbance, like being pushed. X is your state, like all the joint angles and velocities. So your next state is a function of your current state and your inputs and your noise, your process noise. And then you take your state and you're going to have some function of your measurements, because in general you're going to have different number of measurements than states, but there's going to be noise on them. So so the actual measurements will be a function of the states and the noise.
So that converts from what's happening in the physical world to what's the numbers that your sensors spit out.
Yes. Yep. And then the simulated thing, you try to simulate it exactly as the real world is.
Yep.
And if you forget that block, it is exactly the same. And if everything was perfectly the same, your two sensors would say that they're getting the same information. Your correction would say I'm not doing any update, and therefore you wouldn't get any update here.
And what do the purple equations represent?
Now these are your update laws. So you look at, you compare your sensors, so what you think the sensor should read and what they actually read. This will give you some error in your sensors. It's called the sensor residuals, measurement residuals. You multiply that by K matrix to find some delta, some push you want to do on your state. So if your state is saying that, gee, I should be sensing that I'm going 20 miles per hour, but I'm really sensing that I'm going 10 miles per hour, that probably means that my state that represents velocity is too high. So therefore, let's crank back on a little bit. And you won't crank back the whole 100% because maybe the sensor was just wrong.
Okay, so instead of just tweaking the value of our simulations, like we were before with adding and subtracting, we're actually changing the dynamics of the simulation based on the...
You mean by changing these to pluses?
Yeah.
No, all this is doing is saying how we're going to compare that we're comparing the measurements differently, and we're comparing, and that we're making corrections differently, and not necessarily just adding, we might be multiplying corrections. So we might say, hey, we're off by a factor of 2,
okay,
therefore
so
double it, rather than we're off by 3.0, therefore at 3.0.
Okay, so all this is doing is allowing us to do more different operations to allow for more complicated equations,
right?
Like the quaternions you're mentioning.
Exactly.
Okay.
Yep. Yep. Where comparison isn't just subtraction anymore.
But it's still
really
fundamentally the same thing as just reading out error, adding and subtracting. But
yeah,
it allows for more complicated equations.
Yes.
Okay.
Yeah.
That's what I was.
So what we had done, part 2 was a linear Kalman filter. Part 3 was non-linear, but where these two blocks were still linear. And now part 4 is where we also make these non-linear, which adds another level of complexity.
Basically, you need to do this
But
when your measurement values have linear have dependence on each other. The constraints on the values they can take.
Yeah, either when the measurements do or when the states do.
But whereas switching from linear to nonlinear changed the types of dynamics that can occur, all this particular change does is allow for more complicated types of math in the system.
Yeah, the dynamics are still still this stuff.
Are still fundamentally the same. Okay.
Yeah, it's just how you're defining your error.
Okay.
It's different when doing your updates.
On the C being the inverse of D, does D appear anywhere in the flow diagram?
No, it's not showing up in the flow diagram. It's just when we say there's an error, normally it was implied that the error meant to subtract these two signals.
Okay.
Either these two or these two if you're doing your minus error or your plus error.
Okay.
So now instead of subtracting these, we're doing some function on the two. So we might be dividing them
So
in the case of quaternions.
I see a quaternion-based comparator
Yep.
block.
Yep.
Why is this comparator block
Why are
not
there
in the
two of
flow
them?
diagram?
Because it's going to be similar to this if your measurements are just your states, but it's not necessarily the case that your measurements are just your states.
That part's understood. I'm just asking,
Right.
is there?
It's just because the error doesn't show up in this flow diagram. You never know what the error is, right? You just,
So that's just for us to say.
yes.
Given an error, we can infer.
You cannot measure the error.
You can't measure the error because you can't measure the state. I mean, we could. Okay, let me just
Okay.
make
Okay.
a,
Now that makes sense.
let me
That's a
just
good answer.
do D here.
You measure the error. You have.
If we feed
You
this
don't
in
need to do
here,
this.
and this guy in here, then the output of here is E.
But it's in a different
plus
color because
one
it's not part of the flow
minus-
diagram. It's just a definition.
Yeah.
Understood. Okay.
Yeah, I mean, that signal doesn't go anywhere. It never. So these things are kind of being computed because it's the real world, okay?
Right,
And this
right.
is an actual number that you measure. These things are being computed because it's inside the computer and you're actually doing this computation. This number is never computed. It can't be because you don't know what the real.
But it's important to
numbers are.
define that abstraction.
Yeah.
Okay. Thank you.
Okay. So, so if we switch to this board, and I'm going to just notice I have a question mark here because I don't think this is right. There's going to be a different set of constraints. So this is correct here. But I don't know about these constraints. Okay, so I'm not going to derive this stuff. It takes quite a while, and I just make mistakes. I'm just going to put the answer down. But the main thing is that by adding the comparison block and the other block, if you do your partial derivatives right and a couple more get added in here, you still end up with the same error dynamics. So you can still use everything that holds with a linear Kalman filter, even when you have a nonlinear Kalman filter with nonlinear updates. And in all of the cases, whether it's linear, nonlinear with linear updates, or nonlinear with nonlinear updates, this will hold true as long as the way you define all these matrices is this. And we'll go over what this means. So,
Change anything how you calculate K? The change of.
no, K you still calculate the same way, either through pole placement or some other system dynamics way, or by propagating covariances and figuring it out using the Bayesian type logic.
Before we go there,
Yep.
in the error definitions and constraints
Yep.
with the question mark, the two ones that are circled, I'm just very pedantic, but just very simply, I see X and X rather than X hat, and then I see X and 0.
So
What goes
so
behind
let me
that?
go over this. So the error is just the D function, some difference function between X and X hat.
Okay.
So they're just subtraction when you don't have a general, when it's linear.
Okay.
And then the correction term is going to take some, if you have X hat and you correct by this E, then you'll get X again.
Okay.
So these two are both, by definition, kind of the way things go.
Okay.
What this meant was, if you look at if you have two signals that are exactly the same, if your state and your estimate are exactly the same, then your difference needs to be 0.
But that should be
But
an X
that's
hat?
not the case.
Or is it an X estimate? I'm just on the notation on the second
It
end.
just if this
If
was
X is
anything,
X,
if
it's
this
obviously
was
0.
squiggle and squiggle.
Okay, okay,
This
so
is,
that's just
you know, anything and
identity.
anything,
Okay.
but that's not. Let's just erase that.
And what was the C and X0 meaning? If there's no error, obviously, there's nothing to.
Like that.
That is not true for quaternions.
I'll figure out what those constraints actually should be. I think they're a function of both C and S.
Okay.
or something like that, or C. I don't know. But this definitely holds.
Okay.
Okay. Okay, so all I did on this board was repeat all this stuff from over there in equation form. But here's kind of the key right here. Let's go through these one at a time. So this F matrix is the partial derivative of the next error minus, so before the update step, with respect to the previous error. Okay? So if we go back to the board here, what that means is if you're looking at the previous error, so that's how these two compare, based on this function d, and you have a little bit of an error, a little bit more, a delta in that error, then that's going to cause a delta in the error after you do the update step, right? So that's just kind of the derivative of, yeah, it's going to be, yeah, exactly that. So you move the error before the dynamics a little bit, and then the error after the dynamics will change a little bit. So with a linear system, this F is just that matrix F, right? Because if you're just taking with a linear system, you just take x in, multiply by this F, so this x in, and then this gets you x at this one. Right? So it just is a matrix, and that's why we just use the same F so that all this stuff holds true. H is going to be, if you look at the error, the n+1 error before the update, and twiddle that a little bit, how much your residuals will change. So back to the diagram here. If you look at the error between these two signals, and you change that error a little bit, then it'll propagate through here and change this a little bit. So you're looking at for the derivative of that with respect to this error changing. It would actually be the signal here that we added. If that signal's changing a little bit, how much does that change a little bit? So that's H, and again with a linear system, H is just a matrix to start with. So it's pretty straightforward. W is if you change your process noise coming into the dynamics a little bit, how much will that change the error on the output of your dynamics? So back here again, if you have this signal vary a little bit, that'll change the output of this a little bit, which will change the error between these two a little bit. So capital W is how much these guys, the error between these guys changes a little bit as this guy changes a little bit. And then capital V is how much your residual changes for a little bit of change in your sensor noise. So back to the diagram. If your sensor noise changes a little bit, how much does that change this guy a little bit? Okay. And with the linear system, we always just had W and V be additive, so these guys were always identity, but it's not too hard to work those in where they're not identity. Okay, so those are the four matrices you get.
And all of those are recalculated on each step in order to keep the linearizations accurate.
Exactly. You have to recompute it every tick. And if you look over these, so you got F, H, W, and V. They fit in here. F, H, W, and V. And then the only thing left is K, which is a function of these four matrices and prior knowledge of the state.
Does K change over the course of operation, or
it changes every tick.
It changes every tick.
Yeah. Unless if you have a linear system and you want like all your poles to stay in the same place or whatever, then K is constant. For a nonlinear system, even if you want the dynamics of this to be the same, it'll change every tick because all these other matrices are changing every tick.
How is it determined? Is it just a direct function of F, H, W, and V, or is it?
Let's see here. It depends again how you want to look at these things. If you're looking at it from a control system point of view, from a dynamic system point of view, then this function here you can compute like the poles and zeros and all that stuff, and the same with like a control system. you can twiddle the knobs on K to place your poles where you want them. Or you can look at it in terms of an optimization problem and find the optimal K to minimize the squared error of E. Or you can look at it from the point of view of every time you get a new piece of information, a new sensor reading, you have to judge how much you're going to trust that amount, that sensor, based on how much you know you can, based on how much noise you think's in it, and based on how good you think your simulation of your system's going. So if I get a piece of data and there's absolutely zero noise in it, then you should do the thing which moves towards, you should do an update to your state such that that piece of data I gave you is perfectly corrected for. It's perfectly,
So
it
you
should have been expected.
So you could actually have sensors that feed directly into K. Like, if let's say you've got some vision stuff going on, you could have things that measure the light or the contrast or glare or whatever, and say this sensor is getting worse, therefore make K less prevalent.
And the way that works, and I've kind of skipped that. We're already on part 4, and I've just skipped that up to this point to just do it this way, but we'll get to that later. Is that if you know the noise covariance on this signal on W and V, then that'll feed through all this stuff based on all these matrices to tell you what K should be for that tick. Right? So in kind of a hand-wavy way of looking at it is if you know that W is really low, so you're not getting pushed around, and V is really high, you've got super sensor noise, then you don't trust your sensors at all. Forget about this, and K will be near 0. Whereas if you know you're getting disturbed really badly so that your simulation sucks, but your sensors are really good, then K should be really large so that you almost exactly correct for the error that you get based on that sensor reading.
And you have some hybridization of those two, so you end up
Exactly.
pulling out. Okay, so that's how those other functions feed into K.
Right.
Because they give you at least a rough idea of how much disturbance you have and how reliable your sensors are.
Right. Yep.
So K is a linear coefficient matrix whose coefficients are the results of our intuitive heuristics.
Well, they can be intuitive heuristics. When you do the Kalman filter algorithm, it gives you the parameters such that, given what you think you know about W and V, that your error is minimized in some least squared sense.
Okay.
Do you ever analyze F, H, W, or V? Like, anyway, like, does it give you any information?
I mean, it could. I mean, it's going to tell you how, like, for example, W will tell you how process noise fits into your errors, but it's probably usually pretty straightforward, just based on the dynamics, right? If you have, suppose you just have a mass, and W is some force on the mass, then in the next tick, that's going to feed into your velocity, right? So there'll be, in that matrix, there'll be some term that says that that gets multiplied by W, that gives you the next velocity, but it won't show it position because it's going to take the dynamics to get from velocity to position. So I don't know if it tells you too much, but what you can do is find from this guy, find the transfer function from little W to error, right? So just do the algebra, take that, inverse times that, or whatever is going to be your transfer function between the two.
Yeah.
So that could tell you a lot. Yeah. And then you can plot the Bode diagrams to show what and that's where this being a filter comes into play, right? You want the transfer function from W to E is going to be a low-pass filter, and from V to E is going to be a low-pass filter. And you want that, you pretty much want it to be 0, but in order to make it be 0, you can't have it, you can't have your cake and eat it too, because you have to either trust your sensors or your dynamics, one of the two. So you can make, if you make it 0 for one of them and really low for one of them, then it's going to be higher for the other. And so it's just that trade-off between if you think you're simulating well or sensing well.
But if you're equally unsure, it'd be somewhere in the middle, the compromise?
Yeah.
Okay.
Okay, so what I have here is if you don't want to do this whole derivative in one step, and want to take baby steps looking at each of the functions, then your F, H, W, and V matrices can be written out like this. Let's just look at the F one. So it's going to be d sub x. So what I mean by d sub x is the partial derivative of the d function with respect to x, so big D sub x. And then where it's evaluated at is pretty important. So d is a function of two variables. So this d sub x should be evaluated at x hat minus n plus 1 and x hat minus n plus 1. So, once you take the derivative and you've got things left over, you should plug in those numbers for it. If it's so nonlinear, then after doing the partial derivative, you still have terms.
On the d of x,
Yep.
where would that be on the flow diagram? I know that it's at the brown case.
It's not. This is just showing how to go from the nonlinear functions to the linearization of those functions.
Okay, so the vertical bar in the parentheses, the notation, what is that?
Yeah. So what this means is you're taking the partial derivative with respect to x of the function d, which is a parameter of x and x hat. Okay, so since it's d over dx, it's the first parameter.
So it's actual state and estimated state. Right.
Yeah, with respect to.
Okay.
And then once you do that, you're going to get some function that will have x and x hat in it, possibly. If it does have x and x hat in it, then you should substitute for x hat. So you should substitute for both of them in this case, x hat minus sub s n plus 1. And I'm not going to get into how this got derived because it's multiple pages.
But it is x hat on both?
Yeah, yeah.
Okay, follow up later, but that's
Because
good.
what you're pretty much saying is, take the derivative of this function, but for all we know, there is no error because everything is being linearized about the point of zero error.
Okay, okay.
In order for
got
there
it.
to be zero error, both of these are the same. What they are is the value right here.
And so that's where it comes in, the d of xx, anything squiggle squiggle, and the squiggle point we choose is the zero error point.
Yep.
Got it.
Yep.
Okay.
And then same with each of these other ones. So
Okay.
f sub x is the partial derivative of f. So your forward dynamics. Take the partial derivative of that with respect to your state term. And then once you have that partial derivative, evaluate it if there are xu's and w's left. Set x to be x hat n plus, set u to be u because you know what it is, and set w to be 0 because we don't know what
We
w
can't know what
is.
it is. It's processing. Okay.
And we assume that it's 0 mean. And same with each of these other ones. Okay. And one thing that's kind of interesting is you have these C sub e's, which are if you take your correction function, so where you take your estimate and some error to get you the new estimate. So C sub e is the partial with respect to e of c. So take this function, differentiate it with respect to its second parameter. Once you have the partial derivative, then plug in for the parameters x hat n plus and 0. And we use that in the big F matrix. But in the big H matrix, we actually have a slightly different thing. It's the same function being differentiated partially with respect to its second parameter. But once you take that derivative, you put in x hat n plus 1 minus instead of x hat n plus. And there, it probably wouldn't matter in code, and I'm sure we don't do it. Well, it's hard to say where we evaluate these in code, but we might have made a simple mistake. But these are so close anyway that it probably doesn't matter to deal with these differently. But when you do the math, it ends up that these are different, and that's where a lot of the confusion on how all this works is how to figure out each of these matrices. I think that's about all I have to say about that right now. But in general, so if you go to kind of the high level summary of everything, would be that if you're doing a nonlinear discrete time Kalman filter with nonlinear updates, the block diagram is going to look like this. What you're doing is just linearizing everything about 0 error. And if you do that and use these guys here, these 4 derivatives of, to get these 4 matrices, then you can use anything you use with a linear Kalman filter, and your error dynamics will be the same. And then it's just a question of how you choose the case. So, any questions?
On a scale of complete deterministic science to interpretive dance, choosing K is right in the middle, or?
Okay, so that's a good question. If you know that W and V are Gaussian noise with a certain, so kind of a couple answers. From the point of view of probabilistic determination of how good your errors are. If you know that those are both white noise, Gaussian noise, and you know what that are 0 mean, and you know their covariances, then there is a way to choose your K exactly, so perfect science, that minimizes your squared error of this guy. You know, if you sum up all your errors for every tick, square them and sum them up, you're going to minimize that.
So that's just statistics, and we already have
statistics, yes, and that's okay. But that also assumes this linearization that we're doing assumes very, very small deltas. So it assumes that your errors are very, very small. As soon as things, you know, as soon as you get a real high noise that pushes you to your nonlinear error, then who knows what's going on? Then it's much more complicated.
Well, what about the interpretive dance side of this question? What about when, like, we don't have exact solutions and we're just like...
Right, let me get to that.
Okay.
So that's kind of the Kalman filter method of doing it. The second way of doing it, when you look in terms of it actually being a filter and being a dynamic system, is picking this K to place the poles of the system. So that, you know, the dynamic system poles using the error dynamics. And this is going to be exact for, you know, anytime you, for small deltas again. So the actual dynamics for small motions will be exactly where you place your poles. So that's kind of exact, you know, whether, and that's using any sort of control theory technique, either pole placement or, you know, LQR type things where you, which again, we'll do some sort of squared error minimization, or, you know, there's a handful of other things. But it all assumes linear, but it's exact science.
So you can make a surface between sensor and whatever, and change your plots.
Yes. So now the interpretive dance thing is really what we're doing, because we don't know anything about W and V. Maybe, you know, sometimes V is kind of Gaussian noisy, but W is things like the robot being pushed, and that's definitely not a Gaussian thing. So what you typically do, or sometimes do, well, sometimes what you do is say, oh, well, we can come up with, you know, good estimates of what those Gaussian parameters are, so that they're bounding something or whatever. But it's really guesswork. The other thing you can do is just put knobs on your trust of these two things. So you just say, I've got this crank where I trust my sensor, you know, for each sensor, how much I trust it, and for each state input, how much I trust it, that we're tracking it, and play with those knobs until the resulting motion, or, you know, you just, so here's what you can do is,
In Jacob W, then that means that you trust your sensors more.
Right. Let me transport it. So if you're sailing,
Nice video.
and you're learning Spanish.
So, quick question while you're erasing.
Yeah.
I've seen a technique used before where if you have a system like Vicon, where you get more sensors which are quite accurate, but
Yeah.
you don't have that all the time,
Right.
you can use that to help tune K.
Yeah.
Is that a valid thing
Yeah.
that gets
Yeah.
done a
If
lot?
you have ground truth.
Or something that's closer to ground
Right.
truth.
Yeah. So
You can throw both of those in and let K kind of adjust itself over a period of running.
Yep.
K is usually adjusted with the non-linear system, right?
Yeah. So one thing you can do, right? So again, you have these knobs on W and on V, and and you can have one for every sensor and one for every state. So you can say you're interrupting each state, or sometimes if you have like a mass system, you might just say that the W is just a force. And so again, that's only going to, on the next step, it's only going to change an X dot. So it could just be one W even though you have X and X dot, even though you have two state variables. Okay, but what you can do is look at a signal. Look at, here, what would be a good example here? Let's just do this system here where you're measuring the position, X. It's the only thing you're measuring. There's some noise on it, and there's something pushing it around. And then you also have your input. And suppose you can simulate this, and you can change W, right? So what you can do is, your mass is just sitting there. Give W a big push, which will cause, let's see here, if you look at X.
How are we pushing W? Why not just pump with U?
What's U? What's W?
Well, because your estimator knows that you're doing U, so if all of a sudden you make your mass move because of U,
oh, so this is
you.
a way to see what happens with the error, not
Yeah,
not a,
yeah.
okay.
So give it some push in simulation.
So
and
use
that's
what we're
gonna
doing
cause
already,
it.
and W is what happens to us that we don't know?
U is our control, W is external noise.
Okay.
Okay, so W would normally make it go like that, right? And if you find that, and then maybe you do W for a while and then stop. Okay? And so if you also look at V and T, velocity is 0, all of a sudden it's increasing and stops, right? So that's what your simulator is saying ground truth is. And then if you look at what your estimator is saying, if you're seeing this, something like that, then that would mean, what would it mean? It would mean that you're not trusting your sensor enough, because your sensor is saying, whoa, you're way off, buddy. But you think you're not accelerating because you don't know about W. The estimator doesn't know about W. Your ground truth knows about W, your estimator doesn't. So it's not trusting its sensor enough. So then you say, you know what? Trust my position sensor a little bit better. So then what would happen is, and suppose you have some noise on the signal, right? So now if you say trust your position sensor better, now it might start getting better. Say you crank that way up. Now you might be right on, but you've got this huge noise. Right? If that noise is tolerable, then you say, great, I'm good to go, just trust my sensor. If it's not, then you have to choose something between. And that's really what it comes down to is the trade-off. It's really a trade-off between delay versus noise.
As with any filter.
Exactly. Yeah, as with any filter.
You can also have like little settle. You can use settling time or so.
Yeah, I mean that's going to delay, right? Settling time. Yep, so you can do things like, you know, just make it so that some signal is supposed to do a square wave, and then see what happens, or do a step, and then see what happens to it. You know, that versus that versus that, and it's just like control system tuning. And so yeah, so keep saying the example of in humanoid control, bipedal walking, your disturbances are things like being pushed and your foot slipping. So that's another thing you can do, is just all of a sudden make your foot slip a little bit by just, you know, turn the ground friction to 0. Yeah, turn it to ice for a split second so that it slips, and then stop it, and then see what that does to your center of mass. If your center of mass is going crazy, then you should probably trust your sensor a little bit more. If it's not, then so that's where the art comes in.
Are there routines for letting a robot with a control system like this experience different situations and refine its K-metrics and quantify those things?
I'm sure people have worked on it, probably. Yeah, and also, well, if we go back to the diagram here, as far as Johnny's question about like learning and adaptation, in all of this we've been doing so far, we've assumed that F is exact and that H is exact. You know, when we use it in our estimator, we know exactly the dynamics of the system. We don't. There's going to be changes in that. That's one place where learning can come in, is learning F and H. But being robust to those changes is a whole another ballgame of analysis, and we're not going to get into that it gets really complicated.
Or a week or two till we get a real robot to work.
Yeah, so there's a lot of places where you're making assumptions that just completely are not true at all, but they work.
So is this kind of illustration of the Bode plots changing based on sensor versus input, defining the surface? Is that what we're saying that K is doing?
Yes, let me draw something like that. So if you're looking at like your Bode diagram of how much your error changes versus supposed noise, and I'll draw these kind of in a continuous time, even though everything's discrete. So if you have frequency versus EOS, so you would like, let's see here, high frequency noise to be attenuated, right? So you want this thing to be really low at high frequencies. At low frequencies, there's really nothing much you can do, right? If you have a sensor that just says, hey, I'm off by 5 continuously, then you're going to trust that after a while, right? You could put a bias term in it, but if it's really slow. So I think what these guys are going to look like is low-pass filters between going from B to E. And then if you look at going from W to E, so a disturbance, it's pretty much going to be the same thing, right? No, it's going to
Be the reverse, right?
be the reverse, because a low frequency disturbance you can reject.
With
Just
control
integrate
systems,
against
you always
it.
look at the process sensitivity and the
Yeah.
system.
Is that what this is, process sensitivity?
Yeah, I would say yes.
And so does it typically look like that then?
No, both exactly the other way around.
Both are low pass?
Process sensitivity is low pass, and the sensitivity is like you draw on the bottom, I would say.
No, if you do W slowly, you can reject it, but if you give it a quick
Yeah,
push,
if you do
give
W
it an
slowly, you
impulse,
can
it
reject
goes
it.
bonkers.
Have I drawn this right, or do I have these backwards?
Let me see.
If you
Seems
start,
like it should be something like this, right?
you have a pendulum and you start slowly pushing against it,
Yeah.
it will reject it pretty well.
Because you can integrate against it.
Yeah, while if you just smack it, it will just
Yeah.
go crazy.
Yeah,
So-
or,
so
or
we
if
wanna
you're
pay
taking
attention
something
to
and
how
just
quickly-
shaking it really fast, there's nothing you can do except just shake.
Yeah.
So that's why at high frequencies you don't reject W. But sensor noise at high frequencies you just ignore it.
Yeah.
Okay. And then so I think the trade-off here then is that kind of these frequencies are somewhat interrelated.
So this is backwards.
So if you increase one, you have to increase the other.
Yeah, and
Vice versa.
you also have an effect which they call the waterbed effect. Is that if you like want to push down the line somewhere, it grows on the
Grows
water.
somewhere else,
So it's
yeah.
just trade-off.
Yeah, yeah, yeah. So you want them both to be 0. This one you get to be 0 by increasing the bandwidth.
And
increasing
ideally,
where
you
this
just
cutoff
add
is.
sensors till
Yeah.
W is gone.
And this one you want low frequency cutoff, and this one you want high frequency. So
So
that's where the
when
trade-off comes in.
when noise when the sensor noise is important, we want to reject high frequencies, and that's the top one.
Yeah.
And then bottom one is the reverse. Okay. Can, in context of that, could you draw a continuous surface between one and the two as far as confidence between the two? Like a third axis would be W dominance versus V dominance, and so you'd have a transition mapping between the two Bode plots, and that would create a surface,
Probably, I don't know.
right? It's just a morph, right?
Sure. Okay.
Yeah. You need
Well,
a number in the end.
Can you explain a little bit more about the waterbed effect, just what the trade-off is?
Yeah,
Well, it's like it's just that if you wanna, I don't know. It's like you lie in a waterbed. If you wanna push this down, this will come up. That's it.
You get this giant hand in, like near your.
Probably it just
transition
means that the
area.
surface area underneath the curve remains the same.
Okay. And what does that mean in terms of system behavior?
That if you do something up here, it will change the behavior down here. So it just means trade-off.
Okay.
Yeah, if you drop like the slope way down, you probably, if you hit your what do you call it again?
Resonant.
Yeah, your
The cutoff, right.
at your resonance frequency, your system goes bonkers.
Yeah.
Right. Okay.
All right. Any other questions about state estimators in general or anything?
Yeah. So you just want you to have as much information, ideally W is 8, right?
Yep. Ideally, W is 0 and V is 0, but then it's boring.
Did what Jesper said
Net presence
apply to the waterbed effect, that it's
No.
a resonance effect near the point, or that was not
No,
intended?
he's just saying that
Okay. Okay.
The more
that you
sensor-
don't want disturbance. If you want a good estimate, you don't want disturbances. Yep. And you want a good model.
Yeah.
So we'll look ahead from here.
Look ahead from here. Okay, so we didn't really do any examples. What the next thing maybe would be to show how to do this for a real simple orientation estimator, so that we can see how quaternions actually muck things up here.
And could you maybe comment on some of the assumptions you had to make to formulate H or F for the robot? Like how hard is it to do that?
Well, the difficulty is, so difficulty number 1 was realizing that this is what we had, these partial derivatives. And then difficulty number 2 was taking these partial derivatives.
And they have to be symbolic or they can be numeric?
We do them symbolically. He might be able to do them numerically, but it'd probably be slower than doing them symbolically. Since everything is closed form, most of this stuff is so for example, how the center of mass is affected based on the orientation of the robot. That's one partial derivative that you have to figure out. Since the center of mass is a function of joint angles and all this other stuff, you can figure it out close form, but doing so took a lot of effort.
But you do it programmatically. Right? You figure the closed form.
We figured out beforehand, the closed form beforehand, type it in, and then it computes in each tick.
Okay. So you have to do it offline by hand. Basically.
Yeah.
Mhm.
Yeah. It's offline by hand, but it's general to any humanoid robot. It doesn't, we don't have to know the structure of the robot beforehand. We just need to
Two
know
ground contact points.
Yeah, you just need to know, you pretty much just say where all the frames are, and then it uses all the transformation matrices between frames and all the twist computations on all that stuff to compute these guys. So it's not completely hard coded, but
What work
yeah.
on a wheeled robot, for example.
If the I mean it's assuming that you have a sequence of pin joints or a tree of pin joints. Yeah, and that's where most difficulty comes. And then with quaternions in particular, because knowing how, let's see here, for example, this one with quaternions, well, okay, we'll maybe talk about this next, is if you have an error in your quaternion and you got this thing that's spinning, what's your error in the quaternion going to be in delta t? It's really crazy equations to figure out.
Would a brief review of quaternions be in order?